This video will cover how you calculate percent composition and how you calculate empirical formula from percent composition. We've been talking about chemical formulas, how to interpret them, how to go back and forth between chemical formula and name. And so now we're going to talk about some quantitative aspects of chemical formula. First of all, a definition for percent composition. When a chemist talks about percent composition of a substance, first of all, they're talking about percent by mass. That's an important thing to realize. And it's percent by mass of each element that's in the object. So, for example, if you're talking about air, and I think you know it has several different gases in it, and I might ask you, what is the percent of oxygen in all of the components of air? So it's the same type of premise. I might ask you, here's the formula for salt, sodium chloride, NaCl. I might say, what's the percent sodium in a molecule or a mole of sodium chloride? That's I think the most common application of that is the ingredients in almost anything we buy, especially food items. If you look on the side panel of something you're purchasing, most of the ingredients are listed by percent composition. And these percent compositions are also by grams. Notice that the units they're working in are grams. And so, obviously, you need the chemical formula in order to determine percent composition. And then, of course, you need the mass of each element, which you get from the periodic table, that average of mass. And remember, anytime you're doing any type of percentage, all of the individual percentages of the elements in one compound should total up to 100%. You're probably going to want to jot down this formula because it'll be a good reference for you as you're working problems, and ultimately in the test you'll have to have it committed to memory. So if I ask you to calculate the percent of an element X in a compound, the first thing you want to do is count how many of those atoms of X are in that compound. Then you want to look at the periodic table at the average mass for that element. Multiply those by each other because each one of these elements has that mass, and then divide. So this would be your partial weight, and then in the denominator divide by the molar mass of the entire compound. So like anything that's percent, you have part over whole, right? And then of course times 100 to get the percent. A simple example. This is the formula for ethane. If I said, okay, what's the percent carbon in ethane? Again, make sure you do it by mass. Don't just be counting atoms to calculate percent. So the percent carbon, again, is how many carbons are there in ethane? There are 2. Each of these atoms of carbon have an average mass of 12.0, and the total molar mass of ethane is 30. So when I take that fraction, multiply it by 100, I find that the percent carbon in ethane is 80%. You try this one on your own. So I would suggest turning off the video, pulling out a periodic table, and get yourself really comfortable with that formula, and then we can compare answers on the next slide. So this is the answer, or close to the answer you should get. I didn't follow my own rules of sig figs, so if you did, good for you. When you're done, if you're calculating the percent by mass of all elements in a compound, just quickly add up all the percents to make sure that they add up to be 100 and that you didn't make a silly mistake. So let's see, 9, 10, one more, 3, 10... Yep, good. 100%, good deal. So that just is a good check at the end. Calculating percent composition or being given percent composition is really useful for ultimately finding the molecular formula of a substance. So if I bring an analytical chemist a sample of an unknown substance and say, hey, can you please find out what this is for me? They might, in all likelihood, will have equipment that will spit out to them the percent by mass of the elements in it. They'll say, okay, well, it has X percent of carbon, Y percent of hydrogen, etc. I can then take that percent composition and figure out the chemical formula for the substance. I've mentioned before that there are two types of chemical formula, but just to quickly remind you, the empirical formula is the mathematically simplified formula. So just for a quick reminder, the molecular formula for glucose is C6H12O6. If you remember calculating empirical formulas in class, if you can divide each of the subscripts by the same factor, and you do so, you get the empirical formula or the simplified formula. So just to kind of keep that fresh in your mind. So we divided all the subscripts here by 6 to get the empirical formula. The molecular formula is the real formula. It tells you literally how many of each type of element you have in a compound. So here's the process for calculating empirical formula if you're given the percent composition. This is just kind of a little rhyme. I think I've mentioned before my memory is really poor, so I rely on little memory tricks. So percent to mass, mass to mole, divide by small, multiply till whole. That just helped me remember. It may or may not help you, but those are the 4 steps involved in doing the calculation. So let's go through with one. Here's a substance called para-aminobenzoic acid, and we are given the percent composition of all of the elements in it and asked to find the empirical formula. So jot down these steps, okay? First, we're going to convert the percentages to masses. Then we're going to convert masses to moles. Then we're going to divide by the smallest mole value. And finally, if we don't get whole numbers, we're going to multiply until we do. The first step is the easiest. If you have percentages, let's say 61.31% of carbon, if you just assume you have 100 grams of the substance, then those percentages can just as well represent grams. So step number 1 is simply change the percent sign to a gram sign. Okay? Easy. Step number 2 is convert all of the grams to moles. Okay, we're trying to get a ratio, a mole ratio of each of the elements to each other in the compound. So mass ratios aren't going to tell us much. We need to get them all into moles, so we're comparing apples to apples. So to get to moles, and we're starting with grams, of course, we use molar mass as our conversion factor. Anytime we're going from grams to moles or the other way around, you need molar mass from the periodic table. And then we get moles of all of the elements. Carry your sig figs out. Don't be rounding yet. That was step number 2, mass to moles. Step number 3 was divide by the smallest number of mole. So look at these mole values. What is the smallest value? It is 0.7288 moles of nitrogen. And so we're going to divide each of these mole values by 0.7288. The reason we do this is we're trying to we really want a whole number mole ratio of each of the elements. And so we're hoping by doing this we'll get whole numbers. So let's check it out. Carbon, okay, when we divide by the smallest mole value, we get that there are 7 carbon. And kind of the rule of thumb is if you are within 0.1 of a whole number, it's okay to round. If you're farther away than 0.1, you probably need to do the 4th step, which is multiply until you get whole numbers. So we can round. We have 7 hydrogen. Of course, we're dividing by itself. We have 1 nitrogen and 2 oxygen. So you take all of these mole values, they become the subscripts in the chemical formula, C7H7NO2. That's it. That is the empirical formula. Okay, we don't know the molecular formula yet. Here's one for you to try, and I know how tempting it is to go like, oh, okay, I know how to do this, and just skip to the next slide. Believe me, there are going to be all sorts of silly little things you might not think to do until you challenge yourself to go through the tedious details of calculating yourself. So please turn off the video, try this on your own, and then check out your answer on the next slide. Remember, when you're recording masses, average masses from the periodic table, you want to carry 2 digits to the right of the decimal on your molar masses. All right, so let me quickly go through this. Step 1 was change percent to mass, which I did here. Mass to moles, divided by all their molar masses to get how many moles of each. Divide by the smallest, so the smallest mole value is 3.406. Now, unfortunately for hydrogen, we didn't get a whole number. We got 1.33, and that's too far away from a whole number to just round. So this is where step 4 comes into play. So if you remember the little riddle things, multiply until whole, and that's literally what you do. You multiply each of those subscripts by some integer, so you're going to try times 2. If that doesn't work, times 3. If that doesn't work, times 4. And I don't ever remember having gone above 4. So let's try that out and see which of these integers, if we multiply all of the subscripts by them, will give us all whole numbers. Turns out when we multiply by 3, we get whole numbers for each of them. So just to kind of prove to you that 2 doesn't work, if we multiplied all those by 2, we'd get carbon 2. 1.33 multiplied by 2 is 2.66, too far away to round, and so times 2 doesn't work. So you just kind of one by one go up. And you'll get a hang for what type of fractions require multiplying by 2, 3, or 4. All right, so there's one more thing I want to show you. It's pretty easy to do before we end this presentation, and that is, let's say you have the empirical formula and you want to know whether or not that is the same as the molecular formula. So it's pretty easy to do, but there's one more step if you want to make sure that you have the molecular formula. Let's say that you were given the empirical formula for a compound, and let's say, or that you just calculated it from percent composition, and it was C10H7O2. And you were asked, what is the molecular formula? Okay, you need to be given a little bit more information, and the information you would be given is the molar mass of the molecular formula, the molar mass of the compound itself. And so I'm just going to kind of wing this. I'm going to say, okay, the molar mass is 318.31 grams per mole. And now I'm going to tell you how to see whether or not the empirical formula is one and the same with the molecular formula. If these two were the same, the molar mass of the empirical formula should match the molar mass that was given, right? So let's find that out. So the first thing you do is you find the molar mass of the empirical formula. Okay, so let's see. 10 carbon, each carbon is 12.01, and you have 7 hydrogen, each hydrogen is 1.01, and then you have 2 oxygen, each oxygen is 16.0. And so the molar mass of that empirical formula is 1 159.06 grams per mole. So obviously, the empirical formula is not the same as the molecular formula. So how do you find the molecular formula? The molecular formula will always be a multiple, some whole number multiple of the empirical formula. So empirical formula times 1 or times 2 or times 3. So you need to find what that multiple is in this case. You find the multiple of the molecular formula to the empirical formula by taking a ratio of the molar masses. So the molar mass of the molecular formula divided by the molar mass of the empirical formula, so that would be, let's see, 318.31 grams per mole divided by, what did we find? 159.06 grams per mole. And you get that that ratio is 2. That means the molecular formula is twice the mass of the empirical formula. So let's go back. The empirical formula was C10H7O2. If you multiply all those subscripts by 2, you get that the molecular formula is C20H14O4. Okay, that's the molecular formula. And that's it for this presentation.